Okay, so today's plan is we're going to be looking once again at trigonometric ratios on a Cartesian plane. We're going to go just a little bit further than what we did last class, but it's going to be a more or less similar idea. Let's get going. So today's plan, we're going to review reference angles. That was something we covered a couple lessons ago, but it's always good, of course, to review that. And then we'll review trig ratios in the Cartesian grid, like I just mentioned. We'll look at exact values of trig ratios, which we did last class. That was kind of a weird concept, so hopefully we'll be sure to master that today. And then we'll also look at special triangles, which is something brand new. It's something that's actually on your formula sheet, but we'll get to that when we get to that. Anyway, as we go here, let's get started. So reference angle review. Just recall that these are angles that are between your terminal arm and the nearest x-axis. Terminal arm is always just kind of a fancy phrase for like the arm of your angle, right? So it's the actual like line that you draw to represent your angle. The angle, of course, is between your terminal arm and like the starting x-axis. Like if this was your Cartesian grid, this would be like your starting x-axis right here. Your terminal arm would be here. Your angle is what's in between, right? Anyway, find the reference angle for each of these following principal angles. Principal angles are just the general true angle that we'd use. Anyway, 160 degrees, probably best just to draw that first. 160 degrees would probably be over here somewhere, because keep in mind 90 is right up here and this would be 180. So if this is 160, the reference angle, like the definition says, is between the terminal arm and the nearest x-axis. Well, the nearest x-axis is this one right here at 180. So the difference between those two is your reference angle. Well, the difference between 180 degrees and 160 degrees is, of course, 20 degrees. So we can say theta r, that's the fancy way of saying reference angle. Theta r equals 20 degrees. Next one, 301. This one's a little trickier. Once again, draw a Cartesian grid. Remember that this line down here is your 270. 301 is obviously a little more than 270, so we'll put it about right over here. Again, it doesn't need to be perfect, just as long as you got the right idea. 301. Well, the nearest x-axis is this guy over here, which is usually thought of as 0, but just keep in mind, when you go a full circle, 0 degrees is the same kind of thing as 360 degrees. So our reference angle is the angle between these two. So just the difference between 360 degrees and 301 degrees. If you take the difference between those two, you just go 360 minus 301. Long story short, you get, what am I doing? You get theta r equals, I believe, 59 degrees. Last one here, I feel like we might be beating this to death, but whatever. Last one is 220 degrees. Remember, this is 180 and this is 270, so 220 is somewhere in between. Let's just say it's right there. The nearest x-axis is this guy over here, so we're finding the angle between 220 degrees and 180 degrees. Well, the difference between 220 and 180 is, of course, theta r equals 40 degrees. Hopefully that's pretty clear. Reference angles are super important because when you have a reference angle, that's a really crude diagram there, but when you have a reference angle, you can make it into a right triangle just by like drawing a line to your nearest x-axis. Now, the reason that's important is your terminal arm might pass through a certain coordinate, we'll call it x, y, and then that just means your triangle has a side length of x, another side length of y, and then a hypotenuse of r, which is the length of your terminal arm. Once you have a right triangle, you can do a bunch of neat things with it. You can use Pythagoras, a squared plus b squared equals c squared, and you can also use SOHCAHTOA, sine, cosine, tan. We'll obviously get back into that today too. Here we go. So speaking of which, trig ratios on the Cartesian grid. Trigonometric ratios, of course, are your sine, cosine, and tan. Last class, I remind you from science 10, or math 10, sorry, that you have SOHCAHTOA as being a really useful way of remembering which trig ratio does what, right? So let's start with just a normal Cartesian grid here. We're just doing this just generally here. This is kind of like the one we did last class, where even though you can see it goes through the 0.34, we're just going to pretend it's just going through some random x, y. So again, this side would be your x. This side over here going up and down would be your y. And then your hypotenuse is r, which is the length of your terminal arm. If we're talking about sine of your angle, and remember your angle would be right there, sine of your angle is just going to be opposite, which in this case is y, over hypotenuse, which is r. And again, I know it's opposite over hypotenuse because of SOHCAHTOA. SOHCAHTOA is just a really useful way of remembering which trig ratio does what. Cosine, let's look at cosine here. Cosine from SOHCAHTOA is adjacent over hypotenuse. So the adjacent side of this triangle would be x, and your hypotenuse would be r. Okay. Last one here, tangent. Tangent is the TOA part of SOHCAHTOA. TOA says opposite over adjacent. So opposite would be y because it's across from your angle. And adjacent, once again, is x. Adjacent is usually like the hardest side for people to like identify for some reason, but probably because like opposite is pretty clear because it's like just directly across from where your angle is. Hypotenuse is also pretty clear because it's just the longest side and it's right across from where your right angle is. Adjacent is just like the other side, right? So adjacent is usually the third side we'd identify here. So if you have a hard time identifying that, that's pretty normal, right? It's just the weird side. Anyway, I'm rambling. Let's go on. So here's an example. We'll do this one together. Might as well. Suppose we had a terminal arm passing through the point 1, 4. Find the measure of the principal angle. Let's draw this because I think with a picture it makes a lot more sense. So we have a terminal arm passing through the point 1, 4. 1, 4 on a Cartesian grid is going to be in our very first quadrant here. 1 is x, 4 is y. So we're talking somewhere up here. Again, just a really crude diagram can really help us. Making this into a right triangle always helps. So our right angle would be there. Since this coordinate is 1, 4, we can just say that this side is 1 and this side over here is 4, but we don't know our hypotenuse, our r, right? Now the question is saying find the measure of the principal angle. That's the actual true angle here. Well, the good news is because this is in quadrant 1, our principal angle is our reference angle here. They're the exact same thing. So if we're trying to solve for that principal angle, we just need to use a little bit of trigonometry to figure out what that angle would be. Take an inventory of what you've got on this triangle that we've generated right here. We have the opposite side, which is 4, and we have the adjacent side, which is 1. Think about which trigonometric ratio uses opposite and adjacent. And again, if you have SOHCAHTOA, it should become a little bit more clear. Remember, opposite and adjacent, we're looking for the trig ratio that uses both of those. Well, from SOHCAHTOA, opposite, adjacent, that would be the tan part of it, right? So we'll have to use tan to find that missing angle. Remember that sine, cos, and tan, they always take in an angle. So there's always an angle right attached to it. So we're going to write tan and then theta. Theta will be our principal angle. So tan of theta equals the opposite side divided by the adjacent side. So that'll be 4 divided by 1. Now, we want to get the principal angle out of here. Remember, it's connected to a tan. You can't just divide by tan on both sides because that's not how sine, cos, and tan work. You have to do something kind of fancy called inverse tan. So if you see on your calculator, if you press second and then you press tan, there's something that says tan -1. That's your inverse tan. So if we take inverse tan of both sides of this equation, that'll knock out the tan on this side and just leave theta left over. So long story short, we've got theta equals the inverse tan of 4/1. I'm going to plug that in my calculator right now. Just make sure you're in degree mode. Remember, if you're not in degree mode, you got to press the mode button, which is right next to second, and then scroll down and make sure it says degree rather than radian. So make sure you're in the right mode there. Anyway, so inverse tan of 4/1, and I am in degree mode. We're just going to round to the nearest tenth. It's actually going to round this right up to a whole angle here. It's going to be 76.0 degrees. So the measure of our principal angle, the actual true angle in this case, would be 76 degrees. Now, the reason we say principal angle here is, and I don't remember if there's another question a little later on in this lesson today. If there is, I'll eat my words. But the reason I say principal angle here is if we were in a different quadrant, you would just be automatically solving for your reference angle, because when you make a right triangle, you're just using a right triangle with a reference angle. Getting a reference angle from here is fine, but let's say we found a reference angle of 76 degrees down in quadrant 3. Well, since you'd have a reference angle of 76 degrees in quadrant 3, you would just have to add that 76 degrees to 180 to find your true principal angle. Remember, if you're in quadrant 3, that just means your angle, your true principal angle, is somewhere between 180 and 270. So if you got an answer of 76, clearly that isn't your final answer for a principal angle. It would, however, be a final answer for a reference angle. If that was a question on a quiz or something, it would probably be out of like 2 or 3 marks. And if you just solve for the reference angle, you'd get like 2 out of 3 for sure. So you'd get most of it there. But just make sure you're reading carefully and seeing what the question wants you to find. If it just wants you to find the reference angle, you're laughing. You just have to do what we've done here. But if it wants you to find a principal angle, if you're in any quadrant other than quadrant 1, you'll have a little extra step to do. Okay, so anyway, that's my aside. Let's move on. So next question, determine the exact values of the 3 trigonometric ratios for a reference angle of a terminal arm passing through -4, -2. A lot of words in this one. We did questions like this yesterday. basically the bottom line is the most important parts of this question say exact value. That just means if you ever have to square root a messy number, you just leave it as a square root. We'll get to that in a second. 3 trig ratios, sine, cos, tan, right? For a reference angle, in other words, don't worry about your principal, just worry about your reference, right? Of a terminal arm passing through this point right here. Why don't we draw this? Drawing this principal, or sorry, this terminal arm probably is the easiest way of going about this. So -4, -2, that would be over here. -4, -2, right there. Draw a terminal arm connecting it. That was pretty good. Pretty proud of myself with that one. There we are. We got a right triangle going on. This side is -4. This side is -2. Just by the way, I don't think I mentioned it in yesterday's lesson. It might seem silly to call this side length -4 and this side length -2, but it is actually important to keep the negatives in there. And that's related to that cast rule we covered last class. And I know I'm going to mention cast rule again today, but it's really important just to keep those negatives. It's just when you use Pythagoras or something, you got to watch it with brackets. And I think we'll do that in just a second. Anyway, so we want the exact values of the 3 trig ratios. So that's our SOHCAHTOA, right? SOHCAHTOA. Our reference angle is this guy right here because it's between your terminal arm and the nearest x-axis. So there's our theta r. So right there. Notice we know our opposite side, that's -2. And we also know our adjacent side, which is -4. But we don't know our hypotenuse, which we just call r. So before we even begin this question, in order to get sine and cosine done, we're going to need to find that hypotenuse length, right? To do that, of course, because it's a right triangle, you can just use Pythagoras. So Pythagoras is going to say -2 squared plus -4 squared equals r squared. The brackets around this outside, like before the exponent, are really important, because if you literally just put -2 squared with no brackets, it's going to do 2 squared and then make it negative, which will give you a negative answer. We don't want that, right? We want -2 times -2, which is going to be +4. Same with this one, -4 times -4, that's +16. This still equals r squared. 4 plus 16 is 20, so 20 equals r squared. And then, of course, we want to get r all by itself because that's the length of our terminal arm, so we got to square root both sides. If you square root both sides here, though, the square root of 20 is going to be a messy number. It's going to be 4 point something. And there's no point in having a messy number, especially when we say exact values. So this is where you kind of get to laugh. This is actually easier that we don't have decimals in here. Since the square root of 20 is kind of a gross number, we get to just leave this as square root 20. Awesome, right? So put that in there, square root 20. Now we're ready to roll. Honestly, finding the hypotenuse length on one of these exact value of 3 trig ratios questions, finding that hypotenuse length is often like the most cumbersome, difficult part. Maybe I should backpedal on that. I think, honestly, the most difficult part is just parsing through this question and going, holy smokes, this looks like a lot. In reality, it isn't a lot. It's just a lot of words, because there's a lot of very technical details I got to include in it. Anyway, speaking of a lot of words, I'm rambling here. So let's move on. Sine of your reference angle, sine theta r, equals opposite over hypotenuse. Look at your theta r right here. The opposite side is -2 over your hypotenuse, which is square root of 20. There's one of your answers right there, already done. Next one, cosine. Cosine of theta r equals adjacent over hypotenuse. Adjacent over hypotenuse is cosine, so the adjacent side is -4. Hypotenuse, once again, is square root 20. There you go. There's your second one. Your third one here is going to be tan. Tan of theta r. Remember, tan from SOHCAHTOA is opposite over adjacent. The opposite side is -2. Over the adjacent side is -4. Now, you could leave that as your final answer for tan, but we did one like this yesterday too. This would just be lazy if you left it like this. You can simplify that fraction. First of all, there's a negative on the top and a negative on the bottom. Those negatives are going to cancel out. Secondly, 2 over 4, that's the same thing as 1 over 2. So why don't we just say this is +1 over +2. That's a little bit nicer of an answer. I don't believe I would ever dock marks for not simplifying it, but it certainly makes it look a lot better. The fact that we're saying tan theta r is 1/2 is a lot easier than saying it's -2 over -4, even though those mean the same thing. Anyway, that's all there is to that, right? So exact values of 3 trig ratios for a reference angle, blah, blah, blah. Just really focus on the fact that I'm saying you're finding the exact values. So, keep your square roots of the 3 trig ratios, SOHCAHTOA, right? So you're just doing SOHCAHTOA. You're not calculating anything really. You're just like giving me the exact value. The exact value of sine theta r is this. The exact value of cos theta r is this. And the exact value of tan theta r is that 1/2 right there. Now, why do we care? That's probably a big question in your head right now. Why do we care? Great question. I don't know why we care, to be honest. The whole practical use of all this is to be able to find what theta r is, right? In any single one of these three things that we found, you could find the value of theta r by just taking inverse sine, inverse cosine, or inverse tangent of any one of these. If you want to do it as a side exercise, you can do that as well. You could just say, okay, inverse sine of -2/√20. It should give you the exact same thing as if you took inverse cosine of -4/-20. Okay, anyway, so moving on. This is sometimes we just get you to do this as an exercise, that's all. All right, cast rule. I alluded to this a little earlier today as well. Just remember there's a relation between the sine, positive or negative, of a trig ratio, sine, cos, tan, and the quadrant it's in. The cast rule, for whatever reason, starts down here in quadrant 4. That's going to be your C quadrant. Then this is your all quadrant. This is your sine quadrant. And this is your tan quadrant. What this just basically means is down here in quadrant 4, cosine is the only thing that's positive. Up here in quadrant 1, all of them are positive. A stands for all. All of them are positive. In this quadrant, the only thing that's positive is sine. And then in this quadrant, quadrant 3 down here is tan. So tan is the only thing positive. If we go to that last slide real quick, it'll let me, there we go. Notice the only one of these three trig ratios that was positive was tangent. And that's because it's down here in the T quadrant. Cast, just like this. The only thing that should be positive down here is tan. It's just how it works. It's a good way of just double checking to make sure you got things right. The cast rule, while important, isn't like an end all be all, but it is kind of just a nice way of checking to see if you got an answer that you're kind of supposed to get. Anyway, now perhaps a little bit more useful. I want us to imagine a terminal arm that is only a length of 1. So in other words, we have a terminal arm, our hypotenuse has a length of just 1. These are really special situations. We actually call this something called a unit circle, and it's where, of course, your radius of the whole circle all the way around is just 1. If you had a terminal arm with a radius of 1, since cosine is adjacent over hypotenuse and sine is opposite over hypotenuse, and your hypotenuse is 1, you could just conclude in this very special case that your cosine value is just the value of your x, and your sine value is just your value of your y. Again, this only works if the hypotenuse is 1, but it might be useful for remembering why the cast rule works. Notice up here in quadrant 1, if we have just a hypotenuse length of 1, cosine will, of course, just be your x. Notice x is positive in this quadrant over here, right? Because x starts at 0 here and then goes more and more positive. So cosine would be positive. Since sine is just your y value, notice up here your y value is also positive. So, sine would be positive. And then tan is just opposite over hypotenuse, or sorry, opposite over adjacent anyway. So it's just your y divided by your x. And since both of those are positive, tan is going to be positive as well. If we look at quadrant 2, which in the cast rule would be your S quadrant, notice your y value is positive up here, but your x value is negative. That explains why cosine is negative, but sine is positive up here. It's because your y value is positive. We'll also look at these other two quadrants. This one down here is your tan quadrant. Notice your x is negative over here, and your y is also negative down here. So sine and cosine are both going to be negative, but since tan is y divided by x, both of those are negative. Two negatives will make a positive, right? Last one here, it's the C quadrant. Cosine is positive over here. These are positive x values along this way, but sine is negative, right? Because we're down below the x-axis. Hopefully that makes a little bit of sense. It's just kind of like a, hey, this is why cast rule works. Now, we're going to use the cast rule really quick here. This should go pretty quick. Without using a calculator, state if the relation will be positive or negative. As a matter of fact, let's pause the video right here, and I want you to give this one a try. Guess to see if it's going to be positive or negative. Okay, I'm going to go over this now. Hopefully that didn't take too long. We'll start with sine of 50. So 50 degrees is somewhere over here. Notice that's in our all quadrant. That means sine of 50, everything's going to be positive there. So this one will be positive. Cosine 110. 110 degrees is somewhere over here from the cast rule. That means the only thing that should be positive in this quadrant is sine. Cosine is not sine, obviously, so this one is going to be negative. Tan, 250. Well, 250 is going to be down here somewhere. Notice that's in the T quadrant, so tan, 250, should actually be positive. Last one, sine of 300. 300 is over here somewhere. Notice that's in the C quadrant. Cosine is the only thing positive here. Obviously, we're talking about sine though. Sine is not cosine, so we're going to say negative. If you wanted to double check this with a calculator, literally just use your calculator and say sine 50. I don't know what the answer will be. It'll be a messy decimal, but I know it'll be positive. Same with cos 110. It'll be a messy decimal, but it'll be negative, whatever it is. Anyway, enough of that. Moving on. Okay, special triangles. This is the one actually like new thing today. These are annoying. I'm going to be honest with you, but at least we give them to you on your formula sheet. There are certain triangles that we call special, just because there's very convenient measurements that work with them. There's two special triangles on your formula sheet. I think I put 3, but one of them is like just the other one, like this first one turned around. When you have a 30 degree, 60 degree, 90 degree triangle, 30, 60, 90, you have a relationship in that the opposite side length from 30 is 1. The adjacent side to 30 is square root 3, and the hypotenuse length is 2, or at least some multiple of that, right? So it'll scale appropriately. The whole bottom line with this is sometimes we can use these to solve problems with very special kind of like angles with it, just because we have a known relationship. So even if I just told you the angle and I didn't tell you anything about the side lengths, if the angle was 30, 60, or 45 degrees in this other special triangle, you can go to town on this. You can actually calculate it. And again, it's just nicer than having a complicated decimal side length. You know, at least you can get an exact value from something without actually having any side lengths. Anyway, enough rambling. Let me just show you how this works. Let's say we wanted to calculate sine 30, and I told you nothing else about any triangle, just totally in isolation. I said sine 30. If you ever hear 30 degrees, 45 degrees, or 60 degrees, there should be a little bell that goes off in your head. You should be like, ding, 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 ding. Okay, 30 degrees. 30 degrees is part of a special triangle. Since it's part of a special triangle and we're looking at sine, remember that sine from SOHCAHTOA, sine is opposite divided by hypotenuse. Let's start by, I'll just erase this. Let's start by finding 30 degrees. 30 degrees is right here. We're doing sine of 30 degrees, so that's going to be opposite, that's 1, over hypotenuse, which is 2. So sine of 30 degrees should be just 1 over 2. If you don't believe me, in your calculator right now, you can press sine 30, and it should give you 1/2 or 0.5, right? Now let's try sine 45. Sine 45, right over here, that's opposite, which is in this triangle, opposite would be 1, over hypotenuse, which is square root 2. There you are. Now 60 degrees, 60 degrees is right down here. Opposite would be square root 3 over hypotenuse, which is 2, right? Bottom line is, if you ever see 30, 45, or 60 degrees inside some sort of trig ratio, you can just look at your formula sheet and figure out what kind of side lengths you got going on. A little bit of work to it, but that's about it, right? Let's do these other ones really quick. Cosine 30, cosine 30 is 30 degrees is here. Adjacent is root 3. Hypotenuse is 2. So root 3 over 2 is our answer there. Cosine 45, remember it's adjacent over hypotenuse. Adjacent is 1. Hypotenuse is root 2. Coincidentally, cosine and sine at a 45 degree angle, excuse me, at a 45 degree angle is exactly the same. Kind of cool. 60 degrees, adjacent over hypotenuse. Cosine 60 is 1 over 2 because it's adjacent over hypotenuse. Hopefully I'm beating this to death here. If you want, you can pause the video here and give these other 3 a stab. Might as well do that. Go ahead, pause the video. And now I'll go over it. So tan of 30. Tan is opposite over adjacent. Opposite to 30 degrees is 1 over, oh, sorry, I should circle 30 degrees. Opposite to 30 degrees is 1. Adjacent is root 3. There it is, right? 45, find 45. Opposite is 1 over adjacent is 1. 1 over 1, 1 divided by 1, that's easy. That's just 1. Cool, right? Tan of 60, here's 60. Opposite to 60 is root 3 over adjacent is 1. And root 3 divided by 1, you could just call that root 3. Anyway, special triangles are really weird. Long story short, if you see 30, 45, or 60, you got a special triangle, look at your formula sheet, you can get your side lengths from there. Even if I told you nothing else about the triangle, it wasn't like these other previous ones. Where's an example? Let's say it's not like this example where at least I told you the side lengths. If I just literally told you the angle, you can find your other side lengths, no problem, right? Anyway, I think we're almost done here. Yeah, we got a little bit more here. All right, so exact values, special triangles. This is useful when we know the reference angle. but not a specific point it passes through. So in other words, if I just tell you 30, 60, or 45, you got this. These become essential in Math 30-1. We won't worry about that for now, of course, that's still a year away. But just keep in mind, special triangles, as dumb as it'll seem in Math 20, this is something that actually has a lot of uses in Math 30, which I won't get into today. So here's an example, one of the last examples, I think. Yeah, one of the last examples. Here we go. Here's an example. Find the exact value of the sine, cosine, and tan ratios for a 240-degree angle. What the heck? I just gave you an angle, and it's not 30, 60, or 45. Unbelievable. What a ripoff. Well, let's draw this. Let's draw this first. 240 degrees. That's going to be down here somewhere. 240 degrees. You know what? Let's just draw our right triangle like we always do. There we go. We don't know anything about side lengths. We don't know anything about anything else. But what's our reference angle here? If we have 180 degrees up here and we have 240 degrees as our terminal arm, what's the reference angle right here between 240 and 180? Well, the reference angle is just the difference between those two. So the difference between 240 and 180 is 60 degrees. 60 degrees. Ding, 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 ding. That should be ringing a bell in your head right now. 60 degrees is our reference angle. That is a special triangle. Mwahaha, right? So they do come around every now and then. We want the exact value of sine, cosine, and tan for that 240-degree angle. We can just use the reference angle, but we just have to watch the cast rule. Cast rule is going to say, C-A-S-T, cast rule is going to say all of these are going to be negative except for tan. Let's watch this, okay? Start with sine. Sine of 240 degrees. We can use our reference angle to figure that out for us, right? Because we've got a right triangle here. Sine of 240 degrees is going to be opposite over hypotenuse. If we go back to those special triangles really quick, from a 60-degree angle, opposite will be √3 and hypotenuse will be 2. These are on your formula sheet, so you can use them from there. So opposite of 60 degrees, again, opposite of 60 degrees. Oops, if it's going to let me write. There we go. Opposite of 60 degrees is √3. So √3 is going to be this side, and the hypotenuse was 2. Watching the cast rule, though, this is where cast rule comes into play. Notice tan is the only thing that should be positive here. Let's just stick a negative on this, just for good measure. So sine 240 degrees will equal negative √3 over 2. If you don't believe me, check it in your calculator. Literally press sine 240 degrees, and then press enter. And then also after that, go negative square √3 over 2, and it should give you the exact same answer. So there's one of them right there. Next one, cosine 240 degrees. Remember, cosine is adjacent over hypotenuse. So let's look at what the adjacent side would be to 60 degrees. The adjacent side to 60 degrees is 1, and the hypotenuse is 2. So this will be 1 over 2. But remembering our cast rule, the only thing that should be positive here is tan. So we'll stick a negative on there just for good measure. Nice. Last one here, tan. Tan of, oops, so that was a bad habit. Tan of 240 degrees. Remember, tan is opposite over adjacent from SOHCAHTOA. Oops, wrong way. So if we go back, the opposite side is √3 and the adjacent side is 1. So we'll just say that's √3 over 1, or in other words, just √3. And we don't have to make this one negative because notice tan should be positive in this quadrant. So we'll just say tan 240 degrees is √3. Hopefully that makes sense. Special triangles are really mean, but bottom line is whenever I give you an angle at 240 degrees, just draw it. Always see what kind of right triangle you can get. And if you end up getting like a 30, 60, or 45-degree angle, ding, 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 there should be a little bell that rings in your head and you should be good to go. Last examples here. Oh my goodness. So solve for theta, where theta is between 0 and 360 degrees. That's what this says. So theta could be 0 degrees because it's less than or equal to, but it couldn't be 360. So we're just talking in that range. I'm going to be blunt with you right here. To solve this, you're just going to need to use your calculator. But here's a bit of a trouble. And I know this is going to seem totally different than anything we've talked about today. So this is kind of a different example altogether, but you'll see how it'll connect in a moment. Whenever you are using your calculator to solve for an angle, remember in this case, we want to get the angle by itself. So you're probably thinking, okay, we need to use cosine -1 on both sides. Notice this one here is -1 over 2. Just here's a little heads up. Never use inverse trig. Never use inverse trig on a negative. Now, the reason being is if you use inverse trig on a negative, you're going to get a really bad number, at least half the time. Sometimes you'll get the number you want, but other times you get a really bad number. It's a whole weird thing in math. I'm not going to go into detail as to why quite yet. But just remember, whenever you see a negative number, don't use inverse trig on it. You can, however, use inverse trig on a positive, and you can even ignore the negative on here and still use inverse trig on this. Bear with me for a second. So let's use inverse trig, cosine -1 on positive 1/2. Let me throw that in my calculator real quick. I think I have an idea what the answer would be. Cosine -1 of positive 1/2, and I get 60 degrees. Ding, 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 ding. That should be ringing a bell. That's a special triangle, right? I don't know if a special triangle will be useful because we're looking for theta. But here's where we're going to go with this. We know 60 degrees comes out of this. But because it's negative, that tells us that there's got to be some other quadrant going on here, right? 60 degrees, we can consider that our reference angle. Then we just have to use the fact that it's negative to figure out where on Earth we are. If we look at a Cartesian plane, the cast rule says that cosine is negative in this quadrant, and cosine is also negative in this quadrant. 60 degrees is our reference angle because we used inverse trig on a number we forced to be positive. So that'll be our reference angle. If we had a reference angle of 60 degrees in quadrant 2 over here, we're just coming 60 degrees off of our x-axis. What that's going to be is if our x-axis, of course, is 180 and we're going 60 degrees up from that, that's actually going to take 60 degrees away from it, and we'll say our true angle is 120 degrees. The nice thing is you can always check your work here by just saying cosine 120, and it should give you -1/2, right? But here's the weird thing. That's not the only answer in this question. We could also be down here in quadrant 3. If we have a 60-degree angle down here in quadrant 3, we have to go 60 degrees up from 180. So that means we also would have theta equals 240 degrees because that's 60 plus 180. Once again, you can also try cosine 240 degrees, and it should give you -1/2. So just realize, if we don't know what the angle is, we could very well have two possible answers for what our angle would be. And I know how confusing that would be, but just bear with me there. Okay. Anyway, pardon me, I am still sick, so I'm just trying to get over myself here. I've done well though during this thing. Anyway, tan theta equals 1. Just like before, let's take inverse tan of this. The nice news here is because that's a positive number, we don't have to worry about changing it to a positive or anything. So inverse tan of 1. I think I know what the answer is to this one too, but I always double check just in case my mind is betraying me here. If you take inverse tan of 1, you get 45 degrees. That is going to be our reference angle. Now let's have another look at the cast rule. I'll draw it a second time here. The cast rule says that tan will be a positive number in this quadrant down here, but then also, of course, in the all quadrant up here. Let's start with the all quadrant. If we have a reference angle of 45 degrees in the all quadrant, then that means our true angle is, of course, just 45 degrees. If we have a reference angle of 45 degrees in the T quadrant, notice that that's coming down from 180 degrees. So 180 plus another 45 degrees, that's going to give me theta equals 225 degrees. It's weird, but just realize that when you have a trig ratio equal to some number, it could be in one of two places. If we weren't given any other context, we have to assume that it's in both of those places. So bottom line is, for that first question, we have two possible answers there. In the second question, we also have two possible answers there. This is going to take some practice to get used to. So with that, I want you guys trying page 96, questions 1 to 14. There were similar questions I think I gave you today as well. You can do question 2 today. It says closure in the last couple of minutes. I'd only be if this was in person. Of course, it's been a long enough lesson. Use each other as a resource here. You're really going to need to talk to each other about this. You're really going to need to use the answers in the back of the book. This isn't as cut and dry as it might seem when I'm doing it. At the same time, though, it is still possible. Now, of course, if you get stuck, by the time I get back, I will help you guys. So no panicking on that one. If you have any questions, though, please reach out to me over Remind or over Google Classroom. Anyway, good luck, guys.